Hi friends, welcome to follow up. In this video, we are going to look at problem 2948, make lexicographically smallest array by swapping elements. So in this video, our strategy will be sorting and splitting. So our plan will be the following. First, we digest the problem, and then we explain the algorithm by some walkthroughs, and finally we design the code. Now let's look at the problem digest. So here we are given an integer array of positive integers and another integer called limit. So in one operation, we can choose any two indices ij and swap the two numbers if the distance of the two numbers is bounded above by limit. So this is less than or equal to, right? So we want to return the lexicographically smallest array that can be obtained by performing the operation any number of times. So that's the problem digest. So now let's look at the examples. So the examples are actually very easy to interpret. So here the limit is 2, right? For example, we can swap 3 and 5. And here we can also swap 8 and 9. So we get this result. And in the second example, so we can swap 6 and 7, and also we can swap 2 and 1. But 18 is too far from all the other numbers. We cannot swap 18 with other numbers, right? This is the output. So similarly in this one, example 3, so we have 1, 7, 28, 19, and 10. So the distance between any two numbers are actually greater than 3. Therefore, the return is the original nums. So that's those are the three examples. So the constraints are the following. First, the length of this list can be as large as 10 to the power 5. So which basically tells us we need to think of time complexity when we do the coding. And the limit and the nums are both in between 1 and 10 to the power 9. So that's actually just some range requirements or assumption. So with that said, we are ready to look at the strategy. So our strategy will be sort and split. So this split part, we can actually do the split using different methods. But let's first look at the overall idea. So here I'm going to give a walkthrough of example using walkthrough of the algorithm using example 1. So here is the nums and here's the limit. So first, we're going to do the sort nums. So the purpose of this step is to enable us to split the list into disjoint pieces. So after sort from small to large, or if you like, from large to small, to suit this problem, we sort from small to large. So we have 1, 3, 5, 8, 9, right? So the step 1 will be split the sorted nums. So we just need to see if we can chain elements together according to the limit. So now, because we have sorted this one, then the absolute value will be the latter one minus the previous one in the list, right? So first we have 1. So then we look at 3, because 3 and 1 have a distance bounded less than or equal to 2. So we can add 3 to the group including 1. Then also we can add 5 similarly, right? So, but we cannot add 8. The 8 and 5 has a larger distance. Then we initialize a new group, 8. Then we look at 9. 9 and 8 have a distance less than 2, so we can add 9 into the group containing 8. So this is the split. So we're going to have this split list. So notice that the absolute value of 1 and 5 within the same group is larger than the limit, right? So this is the fun actually is expected, but we cannot include 8 in the group, right? So this is the 1 point. And another step 2 is tag the group, because the purpose of this step is to later we can do the assignment. So there's actually a lot of freedom to tag the group. We just need to make it distinguishable. So for simplicity, we can map all the elements in a group into the group indexing. For example, you can map all the elements 1, 3, 5 in this group to index 0, and this 8 and 9 to index 1. And the last step is to assign and get the return by traversing the original nums. So basically, the idea is that within each of the group, we can always assign the current minimal, right? So for example, if you look at 1, let's see, nums 1 is num 0 is 1, so 1 belongs to this group, right? So we just assign results 0 equals 1. So we have, let's write this, result 0 is 1. So now let's look at 5. 5 also belongs to this group, but the current minimum after we assign 1 is 3, so we assign 3, right? So how do we do this? We can, once we assign it, we can pop it, right? Pop 1, so we get 3. And then we look at so nums 1 is 5, but we assign 3 here, and 3 nums 2 is 3, but 3, the current group has only 5, so we assign 5. So this is the one. And now let's look at none. So none belongs to this group, right? So we first assign this minimal, that is 8. So after we assign, we can do a pop if we like. We have none, right? So if we look at the last one, 8 belongs to this group, but we have none remained, so we get none. So this is the result. So this also explains algorithm. So basically we have sort and split and tag and then assign. So to get a better understanding, let's do another example. That is example 2. So after we walk through this example, so actually we believe you will have a much better understanding, and then we can design the algorithm or the coding. So first we do the sort, right? So after sort, we get the sorted numbers is 1, 1, 2, 6, 7, and 18, right? And then we do split. So notice that the limit is 3 now. So we have 1, 1, 2, but we cannot add 6. We have 6 and 7, and then we cannot add 18. So 18 forms another group itself. So next is mapping, right? So step 3. So here I write 0, 1, 2. So map or tagging. So here we assign 1, 1, 2 to be index 0, and 6, 7 to be index 1, and 18 to be index 2, right? So this is actually just for retrieval purpose when we write the code. So now last step, so assign, right? So let's see the result. So if you look at the first element in nums, which is 1, 1 is in this group. So the current minimal for this group is 1. So we assign it as 1. We look at 7, and 7 is in the second group. The current smallest one is 6. So we assign 6. And then we look at 6. So because we have already popped 6, so this will be, the minimal will be 7. So we get 7. So we always assign within a group the current minimal, right? So now we look at 18. 18 belongs to the last group. So we just assign 18, right? So then we look at 2. So 2 is in this zeros group, but we already assigned a 1. So we assign another 1. So this is the 1. And then we look at the last one, that is 1. 1 belongs to this group, but the two ones are already used. So we use 2. So we get this one. So the result will be 1, 6, 7, 18, and 1, 2. So actually, we can we can pause here, and you can try to design the code by yourself according to the walkthrough of the algorithm. But now, if we want to design one, we can move to the coding and just translate the above analysis into coding format. Let me provide one format of solution. So I guess for this problem, the coding part is not the main part, but the understanding of this part is very important. So here, let me first do one. First, let's get the length of this nums list. So this is just for convenience, right? So we can sort the numbers. So this is actually very simple. Here I'm not going to sort nums in place because at the step 3 I'm going to traverse the original nums list. So I'm going to use sorted to get another new list. Sorted nums, right? And then we want to get the groups. So let's see, sorted groups. So here I'm going to use deck because I want to use pop operations. So I want to pop from left, right? So this is just for some choice. You can avoid to using this, but the collections deck. So originally it has not just the nums 0, right? And then we're going to do the step 1, split sorted nums. So this is actually super easy. So basically for I in range, so because we have used the 0th element, we start from 1 and ending at n-1, right? So we can look at the current nums I and the last element in the last group if they have a gap that is smaller than limit, smaller than or equal to, right? So basically if sorted nums I, right, the current one, because this is a larger one, minus sorted groups, so the last element and also the last one within this one. If this is less than or equal to the limit, means that we can chain them together. So what we are going to do is sorted groups. The last group, we just use an append operation, right? Sorted nums I, the current element. Otherwise, we need to start a new group. So basically what we want to do, sorted groups, append. So another one, collections. So here I'm using deck. So sorted nums, the current element, right? So this way we're going to finish step 1, right? So next let's do some simple tagging, right? So let me just make some annotation. So step 0, sorting, right? Step 1, split or grouping, right? So this finished the first step. Step 2, that is tagging. So for this, it's very simple, right? So we can just use a dictionary, and then for I in, let's see, index, right? This the index is a sorted group in enumerate. The reason we use enumerate is that we want to retrieve the index and we map to the index. So this is just one choice. You have a lot of freedom. So sorted groups. And then what we are going to do is for num in sorted groups. So we map all the elements to the index, right? So notice that in this list, the nums can be the same. Each element can appear multiple times, but it does not affect this here. So we just assign nums to be I, right? So and another point is that if the numbers are the same, let's see 1, 1, for sure they're in the same group, right? So that's why this always work. So we have this one. This is done. So next, step 3, assign and return. So this is now very straightforward. Let's initialize a result, right? So we can use append operation, but you can also use a length end result. You can use assign operation. Both are the same. And again, you have choice. So for num in nums, so here we want to emphasize that we are iterating over the original list, right? So first, I'm going to let's do it in 1. So let's see, result append. First, I'm going to get the group, right? So this is just a num, right? This is the group group number, and then we retrieve this group, sorted groups, right? And then we are going to always assign the smallest one. So we use pop left, right? So once we've done this, so we just need to return the result state. So that's actually, this code is a implementation of the above algorithm. So before we make any further comments, let's first do a test. Yeah, it passes one example, I guess. This is example 1, right? So now let's look at the generic case. So here, group pop left. Let's see. This runtime append sorted groups denum. Let's see. Pop left. Let's see what's the problem here. I guess let's see. Result append sorted groups denum, and then we pop left. So it should be right. Let me see what's the problem here. Results sorted groups denum. Let me see. Let me correct that first. So we get we have n, right? Sort this one, so we get split sorted groups collection deck, right? So then we get sorted nums I minus sorted group -1 less than or equal to this one, and then we sorted group append sorted nums I. Otherwise we get a new group collection deck sorted nums I. This is correct. And then for I in sorted groups. And for num in sorted group, we get this one. Yeah, this is right. And then let's see, append. And let's first get the element to make it right. So temp equals this is d num, right? So this is the group the current nums belongs to, right? So then we get sorted groups, right? So we need to do slicing for this one, right? And then we get this one. This is the group. So then what we want to do, result append. So we do temp pop left, right? Then we do, let's see, check again. It passes one example. Now let's look at the generic case. Sorted group. So here is a problem. The lexicograph smallest. Let me see. For num sorted group denum pop left. Sorted nums, right? So so here I guess I write something wrong. When I initialize this one, so this will be sorted nums 0, right? This will be right. Let's check. Yeah, it passes all the cases. So as mentioned, don't confuse with the sorted one and non-sorted one. Now let's recover this one. So here, result append. So first we get the group name, then we sorted group, this one, and then we do pop left, right? Let's do a quick test. Let's see, sorted group denum pop left. Another thing, sorted group denum pop left. Let's see, integer has no pop left, so here sorted group groups, right? So let's test it. Yeah, it passes one example. Now let's look at generic case. Yeah, it passes all the cases. I guess that's about it for the coding part. So now let's look at let's give a quick summary and make some comments. I guess the logic for this problem is sort of straightforward, and there are several places that you have freedom For example, in step 1. So here we just use a very simple way to split this array. But as hinted in the problem, you can use union find. That's just a choice. I guess it's not necessary, but you have that choice, right? So this is the one. And the second one is tag the group. So here you tag it using we tag it using the indexing, but you can use whatever tag you want. The principle is that you can, when we do the traversal of the original list, you can map to the corresponding group, right? So this is another point that which you have choice. So with that said, basically that's about it for this video. So here we provide one implementation of the algorithm. As I mentioned, so the algorithm itself is crucial. Well, for the coding or design of the coding is rather straightforward once you grasp the idea. So with that said, I guess that's about it for this video. Thank you.